All right, good morning, good afternoon, good evening, whatever it is. Let's start going over this test review. These limits I can probably blast through because you guys, most of y'all did really, really well on these, but hopefully I'll stop and point out a few things here and there. So starting here, they're asking about what's going on at -4, so maybe we should mark. -4, of course, is here. So you can see that's that vertical asymptote. So I was mentioning in class, both 8th and 4th, both periods asked about this. But if you've got a limit tending towards infinity or negative infinity, you can just write infinity as the value of the limit, but technically that's a limit that does not exist. So if you wanted to write that the limit does not exist, that's also acceptable. I've always just said that the limit is infinity, so maybe we'll keep on doing that. So we can see that the limit from the left would be riding along this branch, would be approaching negative infinity. The limit from the right would be riding along this branch, and we tend towards negative infinity. And now because those two limits are both the same, the bidirectional limit will be the same, it'll be negative infinity. So that's piece of cake. Now we are taking limits at -2. So we'll just slide this guy over. -2 is here. You can see this time we've got the jump discontinuity. So that means when we take the limit from the left, we'll be riding along this branch, which approaches -5. When we take the limit from the right, though, we're riding along this branch, which approaches 0. And now because those two limits are different, we would say that the limit, the bidirectional limit there, does not exist. Don't say undefined, say does not exist. Okay, now we've got limits approaching 0. That's here. 0 is a little different. 0 is a removable discontinuity that happens to be defined elsewhere. So the function value is defined elsewhere. Did they go on to ask more about 0? Yeah, I should have broken this down differently probably, but oh well. Let's just grab this so we can keep all the zeros together. Whoops. 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 Okay, that'll be fine. There. We'll tack number 9 in here. Can you see that? I don't know what I'm doing. Excuse me. Okay, now it fits nicely. Alright, I also wonder if elsewhere you're being asked for the function value. Yeah, so 18 is asking for the function value at 0. All of those should be together, honestly. This could have been formatted better, but whatever. I'll just write it in. Don't forget there's a number 18 that's asking you for f of 0. Honestly, you should always have all 4 of these things in mind. Anytime you're evaluating a function for continuity or for a discontinuity at a certain x value, you should always be thinking about all 4 of these things. Left-hand limit, right-hand limit, bidirectional limit, and function value. So the first time we get sort of an interesting result is here at 0, so we'll do it for 0. From the left, we ride along this branch and we get 3. From the right, we ride along this branch and we get 3. So that means that even though the value of the function is 4, the bidirectional limit is the 3, because the bidirectional limit is defined by the left and right hand limits. So since they're both 3, the limit is 3, the function value is different. So we had a question about like this on one of our quizzes that said, is the function continuous here? And if it isn't, then what rule of continuity did we break? Something like that. And so for those of you that may not remember, the rules of continuity are that f of the x value has to be defined. And so for us, it's defined and it's 4. So that's all good. The next rule was that the limit of the function as x approaches c has to exist. And that's the bidirectional limit. So since the left and right hand limits are both 3, the bidirectional limit does exist, and it's 3. And then the last one was that the function value has to equal that limit. And so if you were trying to justify to me that we were discontinuous at 0, you'd be saying f of 0 is defined, it's 4. The limit of f of x as x approaches 0 exists, and it's 3. So the rule that we break, of course, would be this third rule about how the function value 4 is not the same as the limit, which is 3. So that little stipulation there proves that we are not continuous at 0. We in fact have some kind of discontinuity. And because the left and right hand limits are the same, we know it's a removable discontinuity. Anyway, I think you guys knew all that, so moving on. So we already did this limit. We said it was 3. Moving on to the next one at number 1, at x equals 1. Oh, I don't have my little highlight anymore. So this time we're looking at 1. And this is a boring one, because at 1, this function is continuous. Left-hand limit, right-hand limit, bidirectional limit, function value, all of those things are 0. So the function is continuous at 1. So you know pretty much right away. You can fill all these things as 0, 0, limit 0. If they ask for the function value somewhere, they don't, but it would have been 0. Alright, so what about 5? Is 5 a more interesting place? Not that interesting, honestly. It's just a vertical asymptote. It's different from the other one, though, because for the vertical asymptote over here at -4, the behavior from the left and the behavior from the right were the same. They both tended towards negative infinity. However, over here at 5, we see that from the left, as we ride along this branch, we're approaching negative infinity. From the right, as we ride along this branch, we're approaching positive infinity, which would mean that the bidirectional limit does not exist. And now they're asking us to look at these end behavior limits, the limits as we go towards infinity. So for that, you're going to hop on this branch and you're going to run to the left, 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 left. And you can see that we've got some horizontal asymptote that we approach, which is at a y value of -3. So that would be our limit as we go to negative infinity. I assume they're now asking for the limit to the right. Yep. So we'd ride along this branch, and this time we would get sort of stalled out at a horizontal asymptote at 2. So that's that limit. F of 0 we already talked about. It's 4. F of -4 is undefined. Don't say that it does not exist. Limits do not exist. Function values are undefined. Over here at -2, the value of the function would be -5. It would be defined by the dot rather than the whole. So give me the value at the dot. And at 5, we are undefined again. So I think you guys are great at this. You probably didn't need very much help with that. So let's keep moving. Oh yeah, so now they wanted us to say use expressions to classify each discontinuity and tell which x value they occur. So fine, we can run through that. Let's take it left to right. First discontinuity is at x equals 4, and it's an infinite discontinuity. And we may as well kill 2 birds with 1 stone, because there's another infinite discontinuity over here at 5. So there's your infinite discontinuities. At -2, we've got the finite discontinuity, which is also called a jump discontinuity. And that's at x equals -2. And then at 0, we had our removable discontinuity. Which is also called a point discontinuity. And that's it. That's all of them. So there's a vertical asymptote here, vertical asymptote here. There's a jump discontinuity here at -2. And there's a removable discontinuity here at 0. Yeah, so that's it. You'd want to remember how to justify all of those discontinuities using limits, but I think it's pretty obvious. Again, you've got an infinite discontinuity as long as both of the one-directional limits exist, and at least one of them is infinity or negative infinity. You've got a jump discontinuity when both of the one-directional limits exist, but they're different from each other. They have to be different and finite. You can't have one that's infinity, or else you'd have a vertical asymptote. And lastly, To get a removable discontinuity, you need both of your one-directional limits to exist, and you need them to be equal to each other, and then you need the value of the function to be anything else, literally anything else. So for example, you could just have the function be completely undefined. That works too. If I just took this dot away, then this is still a removable discontinuity because the left and right hand limits exist and are 3, but the value of the function we would say is undefined. Clearly 3 is different from being undefined. But when the function is defined and you just get 4, obviously 3 and 4 are different, so that's still removable. That's it. Okay, so now for something different. It says for each function given below, determine the inverse function. And that's fine, we can do this pretty easily. This is the operation where, algebraically, you just change all your x variables into y variables and y variables into x variables. So we said for this cube root function, we'll make that switch, and f of x becomes x. And now we're taking the cube root of 2y minus 1 plus 3. So some quick algebra here, we'd subtract 3 from both sides. And at this point we would already find ourselves wanting to get rid of this radical. And the opposite of cube rooting would be cubing, so this thing would get cubed. And at that point we'd have 2y minus 1. So first you'd want to get rid of the 2. You could divide by it, but my preference, as I've stated before, is to just multiply through by a half. And then I've got this coefficient rather than a denominator. Once that's gone, we see that we'd want to add 1 to both sides, and then that's it. That would be y. Or a better name for it is f inverse. So here's what they're not doing. They're not asking you to come up with the domain, but that's sort of an expectation, is that whether I asked you to give the domain or not, you better give me the domain, especially if that domain has restrictions. Here's the boring thing though. Since the original function is a cube root, not a square root, maybe you know this, but cube root of x doesn't have any restrictions on its domain. The right-hand side looks a hell of a lot like a square root function, the only difference being the rate of growth. For a square root function, 0 gives 0, square root of 1 gives 1, and for a cube root function they agree, 0 gives 0 and 1 gives 1. But for a square root function, you'd only have to go out to 4 to get 2. Square root of 4 would be 2. For a cube root function, you got to go all the way out to 8. Because cube root of 8 gives 2. 1, 2, 3, 4, 5, 6, 7, 8. So suddenly we can see that we grow a hell of a lot more slowly. This graph is kind of garbage, but cube root function is slower. But what's the cube root of negative 1? It's negative 1. What's the cube root of negative 8? It's negative 2. So we can see that a cube root function would have odd symmetry. It would be defined on both sides, and its domain would be all reals. Slightly more importantly, its range would be all reals too. And since its range is all reals, we do not have to put any restrictions on our inverse function. Oftentimes, our inverse function has to inherit domain restrictions from the range of the original function, but that is not the case here. We know that for f inverse, our domain seems like it would be all reals because we're a cubic function, that should be all reals, and it is all reals because the original function's range was all reals. And this function's range seems like it should be all reals because it's just a cubic function, and it is. And that's because the original function's domain was all reals. So as long as you're kind of basing those answers off of the original function rather than whatever algebraic rule you get at the end, you should be fine. So speaking of that, looking at number 2, here's a function that does have restrictions on both its domain and range. You might want to just do it right away. So what's the domain of f? I'm going to put it way over here in this corner. Well, our domain would be all real numbers except for the zeros of the denominator. So it would be all reals except. And then you just figure out what makes the bottom equal 0. So set it equal to 0, add 5 divided by 2, and you see it's 5 halves, the fraction 5 halves. So now no matter what happens algebraically, we know that our new inverse function has to have a domain. Oh, superpsych. It would have to have a range of all reals except this value. But to find the domain, we got to think about our range. And I've walked you guys through this before. Hopefully it'll stick. Looking at this, this is degree 1, and this is degree 1. They're both linear. So that's the case where you look at your leading coefficients, and you know that this graph would have a horizontal asymptote at 1/2, meaning it would never give 1/2 as a y value. So our range is going to be every y value in the world except for 1/2. We're not going to get that value because that's where our asymptote is. So now, what I was trying to say before was, no matter what happens algebraically, we already know that the domain of our inverse function should be this range. It should be all reals, except for the 1/2. So if we get an algebraic rule where it seems like the 1/2 is a perfectly valid input, we still have to restrict it anyway, because the domain for the inverse comes from the original function, more so than anything else. Now, what's our range? Our range should be the original function's domain, which should be all reals except for 5 halves. Whatever. Let's do the math now, see what happens. Let's do it in lavender. All right, change the signs or change the variables. You're going to be x, you're going to be y, you're going to be y. And then, again, I still think the cleanest way to think about this is we're just cross multiplying. So this x will distribute onto this and give you a 2xy minus 5x. And of course, multiplying by 1 doesn't do anything, so we get y minus 4. Then what we said was when you're finding the inverse of a rational function, you're going to end up with a term that has y in it on the left, and then another term that has y in it on the right. And you want to get those terms that contain y together and alone. So I'm going to subtract the y, and I'm going to add the 5x to just get everything together on one side that I want together. So that's going to give me a 2xy minus y. That equals 5x minus 4. Then if I'm trying to isolate y, I don't want there to be two different y's. I just want one y. And the fastest way to turn these two y's into one y is to factor it out. And suddenly, I only have one y that I could distribute back in. That would turn it back into 2xy minus y. So we know we're doing something that's totally legal. But now that we're here, we see we can just divide by that. So we're going to get y. And a better notation for y, of course, is to just call it the inverse of f of x. But it's going to be 5x minus 4 all over 2x minus 1. So here's the good news. We can already see that this function's domain is going to be all reals except for 1/2, because 1/2 would cause the denominator to be 0. So actually the algebra didn't betray us here. The algebra is giving us the correct domain that matches the range of the original. So there's nothing tricky here. This one's normal. And same thing with the range as well, because we would look at this and see the horizontal asymptote at 5 halves. That means that's the one output we won't get. Our range would be all reals except for that. So with rational functions, that whole inheriting the domain of the original function, it kind of happens naturally. You don't even have to think about it. It just happens. So let's move on. So they're not asking about it anymore. Okay, great. So let's pretend for a moment that I was trying to actually give you a review sheet that was useful. I mean, maybe what I should do is pull up the quiz or something. Quiz number 3 had a question on it. Whoops. Quiz 3 had a question on it about finding the inverse of a quadratic. More a radical, but a radical with an even power. So pretend for a moment there was a number 3. Imagine if I gave you like a 4th root. Who cares? And even the numbers don't matter. Put a +7 over there. I don't care. But hopefully you would know that that function has been shifted left 3, up 7. Even if it's a 4th root, it's still going to be just essentially the top half of a parabola. So when you go to solve this thing, when you go to find the inverse and you get some fourth power function, you know that its graph is going to want to have two halves. It's going to want to look like a parabola. But if our inverse functions are supposed to be reflections over the line y equals x, then we know that this top half of a parabola should only be yielding to us a right-hand side of a parabola. And that's it. So when you get that fourth power function and you're thinking to yourself that its domain should be all real numbers, you better fight that urge and remember that the domain of this purple thing really has to come from the range of this blue thing. And the range of that blue thing would only be 7 to infinity. So you would have to restrict the domain of your quartic function to only those things that are greater than 7. I hope that made sense, because that's important. And it wasn't really represented here, so hope you watch in the video. Alright, let's do these. Except let's not do these. I said you could ignore them. Use composition to determine. No, you got to do these. Alright, these are dumb also, because both 3 and 5, you should know right out the gate that these guys are not going to be inverses of each other, because nobody put any restrictions on the domain of this quadratic. So I find myself hitting on the exact same idea I was hitting on 1 second ago. But before you even do a lick of algebra, you should be thinking about this graphically and knowing that square root of x plus 5 minus 2 is left 5 down 2. There it is. There's your graph. It's the top half of a parabola. But the graph of this quadratic is what? Left 2 down 5? But it's a full-blown parabola. And we can see that if we were going to be the inverse of this radical function, it could only be the left-hand side. As soon as you graph the right-hand side too, these things are not reflected images of one another anymore. This graph has a left-hand side, but the green graph has no bottom. That's a deal breaker. So the only way these functions could possibly have actually been inverses is if there was a stipulation up here that said, hey, you know what? Your domain is going to be restricted to only those x's that are greater than or equal to -2. The -2 from inside parentheses. The -2 that becomes the x-coordinate of the vertex of this parabola. You only want everything to the right of it. Again, I hope that made sense. Without that, there's just no way they can be inverses. Now, slightly more trickily, if we put a negative in front of this thing, then suddenly you'd be getting the bottom half, and then you'd want the left-hand side. So your domain would have to be restricted to all those x's that are less than -2. You'd want to pair the left side of the parabola with the bottom half of the radical if it had a negative on it. So there, I think I've talked about that idea ad nauseum at this point. You guys are gonna have to start integrating the algebraic, the graphical, for sure. A lot of what you should understand about functions is going to be coming from the graph more so than from the algebra. So know those graphs, you really need to. But anyway, I think you got to do the math. I'm not sure you could just fall back on an appeal of saying, hey, the domain doesn't match the range. Although if you did say that, I'd probably let it go, but I don't know. I think you better do the math. Let's put a line here. See how this goes. Let's put a line here. And let's do these. Where are we at? It's 24 minutes into the video. I don't know if I'll cut the video up. I probably won't. You guys, some benevolent soul can put in timestamps or something. Put in timestamps. Be nice to your fellow classmates. Alright, forgot to erase that negative sign. So you guys know that to use composition means you've got to do m composed with n and n composed with m. And you also have to do n composed with m. So if we're plugging n into m, that means the radical's getting plugged in here. So you would get square root of x plus 5 minus 2. That's going to be your x. So that means we go plus 2 all squared minus 5. So there's your n of x inner function inside of the quadratic. So what do we always say? We say these parentheses aren't doing anybody any favors. They can go. These things cancel. You're now squaring a radical. What happens when you square a radical? Well, when you square a radical, if you want the radical to just go away, giving you x plus 5, you would have to restrict this thing's domain. You'd have to restrict its domain to only those x's that are greater than negative 5. Then you could cancel these, and then you could get x, but you'd be getting x on a domain that's restricted to only those x's greater than or equal to negative 5. And that's true for the radical function. That radical function's domain is kind of restricted anyway. So honestly, I think for m of n, I think this is working out fine. We are getting x. We're going to fail when we do it the other way. Because suddenly this time, we're going to plug the quadratic into the radical. So we're going to go x plus 2 all squared minus 5 all bracketed in. And that's getting crammed into the radical function. So there'll be a big radical with a plus 5 inside of it and a minus 2 outside of it. And again, these outermost brackets, they're not necessary. Kill the 5s. We're now taking the square root of something squared. And those of you who remember will remember that this is x plus 2 absolute value. And that's just not really going to go away because our inner function is this quadratic, and our inner function has no restrictions on its domain. So we'll be plugging in some values that yield negative answers. We'll be plugging some that yield positive answers. These absolute value bars, though, are going to turn everything positive. So this just doesn't work. I can't take the bars away, so I can't cancel the 2's. So we land here. We can't reduce any further. And so we can definitely can conclude that m and n, as written, with no domain restrictions, are not inverses because this composition did not boil down to x. Among other reasons, but that's a reason. All right, ideally number 4 is going to work out nicely, so let's just do it quickly. This one is the one that's really algebra rich, so you have to make sure you know how to do this. Let's do g composed with r first. So we're plugging function r into g, which means we get 2x plus 7 over x minus 1 plus 7 all over 2x plus 7 over x minus 1 minus 2. So we know that to add these fractions, you put that over 1, and you need a common denominator. So you multiply by x minus 1 over x minus 1. But to subtract these, you put this over 1, and then you need a common denominator. So you're multiplying this by x minus 1 over x minus 1. So then we clean this up. We've got a big fraction whose numerator is a big expression, whose denominator is a big expression. But both of our denominators, once we've got a common denominator of x minus 1, your denominator is just going to be the x minus 1. This denominator is just going to be the x minus 1. And guess what? When the two denominators of a complex fraction are the same, they're just going to cancel out. So there's almost no point in even wasting the time to write them down, because all that's going to matter are the numerators. And our two numerators are the 2x plus 7, and then distributing this 7 gives an extra 7x that we're adding on, and then an extra 7 that we're taking away, so minus 7. In the denominator, we've got the 2x plus 7. We're distributing a negative 2, so we're taking away 2x, and we are adding on 2. So our whole fraction really is just this red stuff. Let's turn it into orange stuff. So our numerator is going to be 9x, and the 7's cancel. In the denominator, the 2x's cancel, and 7 plus 2 makes 9. Cancel the 9's, you just get x. And that's it. I'm not done, of course, because we only did Q composed, or G composed with R. We need to now do R composed with G. So I'm going to take all this away. And you guys know if you need to see it, you'll just pause the video. When I say take it away, I really mean shoot. What I really mean is I'm going to shrink it down to a super tiny size. And then if I need it, I can bring it back. But you guys can just rewind the video if you need it back. So we're now doing R composed with G in that order. And the algebra is going to feel almost exactly the same. That's right? Yeah. So we now have a coefficient 2 in front of x, which is this whole rational, x plus 7, x minus 2. And we're adding, we're adding 7 on. Then in the denominator, it's just x minus 1, so in goes the x plus 7 over x minus 2, and then no minus 1. So we kind of saw this already. You should be thinking you're going to get a big rational expression. You're going to have fraction over fraction, but the denominator is going to be x minus 2, and the denominator's denominator is going to be x minus 2. So those guys are going to cancel. So essentially you're just going to take the 2, distribute it, and get 2x plus 14. And over here, to generate your common denominator, you're going to be multiplying by the x minus 2. X minus 2. So you'll distribute in the 7 to add on 7x and take away 14. That's your numerator. I don't know that I need to see the denominators. We know they're going to cancel out. So what's happening downstairs? You'll get the x plus 7. And you'll multiply by x minus 2 over x minus 2 to get that common denominator. Now don't forget to distribute the negative. You're going to get negative x. It's not going to be minus 2. It's going to be plus 2. So there. But from here we're in really good shape to just clean this up. We can see the 14 and the 14 cancels. We get 9x in the numerator. In the denominator the x's cancel. 7 and 2 makes 9. Cancel the 9's. There's your x. So up here, this little teeny one, we did our composition, we got x. Here we did our composition, we got x. So we can state for certain, therefore, g of x and r of x are inverses. All right, and number 5 is going to be the same as number 3, so it feels bad. I don't even really want to do it because it's so much the same, but we know right out the gate that these guys are not going to be inverses of each other because there's no restriction on the domain of the quadratic. So they couldn't possibly be, because this quadratic is going to be a full parabola and this radical is going to be half of a parabola. They're just not going to really be true images of one another. I'm not doing it. I'm not going to do it. I'm going to say the same exact thing is going to happen when we plug the quadratic into the radical. So when we do g composed with f, it's going to fail. Because when the quadratic goes in and we take the square root, it will generate absolute value bars. And then all of our stuff won't cancel. So they're not going to be. They're not inverses. I'm taking a shortcut. You shouldn't. You have to actually do that. Moving on. All right, use your knowledge of composition to decompose into two functions f and g, such that f composed with g would be equal to h of x. This is really easy, but it's that thing I told you did not have to do. But just for the sake of having you well prepared, you want this to be f of g of x? All right, I think it's pretty obvious. I see an outer function that is these absolute value bars. So absolute value of x. I see an inner function that is this linear expression, 3x minus 5. And we're done. You can take that, plug it into there, and you're done. Piece of cake. This one, same deal. My outer function f would be just a plain old x that's getting squared. plus 3 times a plain old x. And then the function that's getting plugged in there is the x minus 1. And then hopefully you can see, if I took that, plugged it in, I'd have the x minus 1 squared plus 3 times x minus 1. That's what decomposition is. It's a piece of cake. Even for something like 8 that involves sign, you still should look at this and just be getting that f of x is the outer function, g of x is the inner function. So who's the outer function here? Sine of x. Who's the inner function that got plugged in? X squared plus 3. I really feel this is quite simple, but it won't be on your test, so you can ignore it. Alright, now it's time for function operations. This stuff's always a little tricky. They're starting you off with a quotient, so you'll grab h of x, 3x plus 5, and you'll just divide it by f, which is that radical. And you can't really simplify this because the days of worrying about radicals in the denominator, those are gone. It's now considered perfectly fine to leave radicals in your denominator. So there's your function rule. There's your expression. But what's our domain? Well, we got to do two things, honestly. We have to satisfy the domain of the function that we see here, but we also have to satisfy the domains of h and f. Luckily for us, h has no domain restrictions at all. The only domain restriction on f is that we would need to be greater than or equal to negative 8. Well, we see the same radical down here, so we know that we're at least restricted to being greater than negative 8. But notice that because the radical's in the denominator, even though normally you can take the square root of 0, remember that plugging negative 8 in here will give us square root of 0, and we'll get 0, and now we're dividing by 0, and dividing by 0 is bad. So because we ended up doing a quotient problem, a division problem, the guy that normally doesn't mind taking the square root of 0, well, he gives an output of 0, and this function does mind if you try to divide by 0. So quick fix, you just make the hard bracket into a soft bracket, and you live happily ever after. This will be the correct domain for part A. Now for B, what are we doing? We're plugging a radical into a quadratic. Okay, fine, can do that. So that'll be 2 root x plus 8. All squared plus 4. Alright, we're squaring a radical. Neat. Square it, it cancels out. Plus 4. Distribute the 2. Add 20. Factor the 2 back out because I want my final answers factored. There's your final answer, nice and clean. But I believe I was harping on this not too many minutes ago. Don't we have to take into consideration the domain of the inner function? Well, the inner function has a domain. It says you can only use things that are greater than or equal to negative 8. So that's going to be this guy's domain. And is there anything else for us to care about? Not really. The only other thing we would consider is the domain of the actual rule that we got, but this thing's linear. Its domain is all reals. So we do need to take care to respect those domain restrictions on f, but they're fine. And looking at function g, there's no domain restrictions on g, so we wouldn't have to worry about it. Let's do f of g of x now. This time we're plugging the quadratic under the radical. And you guys should already know how this goes because we already talked about it twice in just this video. But we're now doing 2x squared plus 4 plus 8. Okay, so I've got a quadratic under a radical. And stuff doesn't just cancel out this time. It's not just super clean like that. So how do you attack a problem like this? Well, first of all, I see everybody's divisible by 2. So I can certainly at least factor out a 2 to make everything else simpler. That should be an x, right? Or it shouldn't. Okay, hold on. Then we should simplify first. I thought that was an x. But we're going to have 2x squared plus 12. My advice is still factor out the 2. And that's the best you can do. That's it. Now to come up with the domain, we've got an inner function that's quadratic now, so there's no domain restrictions. We have an outer function now that is a radical. So we could not allow anything under the radical to be negative. But here's the deal. Algebraically, solving for values of x that would make this greater or less than 0 is a nightmare. But graphically doing it is a piece of cake. Because, you know, this is just going to be the graph of x squared. I feel like the 2 happens first. I feel like it doesn't actually matter. But we're going to get shifted up 6. That's what's really happening here. Yeah, we're going to go up 6. Then we're going to get shifted or vertically stretched by a factor of 2. So I'm wrong. We want to be vertically stretched by a factor of 2, then shifted. Not that it matters. But we should have a skinny parabola stuck to the y-axis, basically. And we can see what? We can see that graph, what I'm graphing right now, by the way, I think I'm being unclear, but I'm graphing this quadratic only. None of the radical part is involved. But you can see that this quadratic function has no negative outputs. It's always greater than 6. So even though we've got this function that's nervous about negative inputs, the function that we end up with under that radical is a function that never gives negative outputs anyway. So we know we're safe to just call the domain of this function all reals. Hopefully that made sense. I'm going to move on. Another composition. This time we're cramming function h into function m. Okay, so function h has no domain restrictions. Function m is restricted to where x can't be negative 3. But if you're in a hurry and you just tell me that the domain is all reals except for negative 3, you're going to be wrong. Because with m as the outer function, h of x happens first. So if you plug in negative 3 to get negative 9, plus 5 is negative 4. Negative 4 is a perfectly valid input for function m. So there's nothing wrong with negative 3 as an input in our composition because it funnels into h first. And it doesn't come out as a negative 3 anymore. It comes out as a negative 4. And negative 4 is a perfectly valid input. I don't know why I'm saying negative 4, by the way. What are we plugging in? Yeah, okay, it comes back as negative 4. So really the restriction on our domain is going to be something else. It's going to be whatever number 3x plus 5 actually uses to give the negative 3 that is bad. So solve this equation. 3x equals, subtract, negative 8, divide. It's negative 8/3 who's bad in this function, and you'd never see it. That's not evident in the function rule for h or for m, right? But here's why. You take the negative 8/3, you plug it in. Negative 8/3 times 3, the 3 cancels, you get negative 8. Negative 8 plus 5, you get negative 3. Now you're shipping that negative 3 off into function m, and we see that negative 8/3 is actually the guy that causes us to plug in negative 3, get 0, and become undefined. So negative 8/3 is the guy that we need to restrict from our domain. Now all that said, I'm trying to do that without doing a lick of algebra. I'm trying to do that by just basically thinking it through. So I guess I'm doing algebra. I'm trying to find the value, but it's really simple algebra. The flip side is just do the algebra from the get-go. Just actually find the rule. Oh, find the rule, and I think that the domain restriction is actually obvious anyway, so you don't have to do any of the weird finagling that I did. But we're going to plug h in, so we get 1 over x plus 3. And that x variable is going to be h of x, so 3x plus 5. And again, those parentheses aren't doing anything. So our final function rule is just 3x plus 8. And then lo and behold, the domain was always going to be all reals except the 0 of the denominator, which is negative 8/3. So I don't know. I think maybe I gave you a slightly different take on this, a different way that you could think it through. But I think the long and short of it is just stick to the algebra anyway. This one looks easy. This is a sum. And by the way, it's a sum of a function whose domain is all reals and another function whose domain is all reals. So before you do anything, you already know this function's domain is going to be all reals. But we'll go 2x squared plus 4. And then we're adding to that 3x plus 5. And that's going to end up giving us a quadratic, so 2x squared plus 3x plus 9. So the question is this factorable? And I don't think it is. We go 2x, we go x. 2 times 9 is 18. So you're looking for factors of 18 that give 3. 3 and 6 probably shoot to mind, but it's not a plus minus. We've got 9 as a positive, so it's either minus minus or it's plus plus. And neither of those are options. So what else is there for 18? We could do 1 and 18. That's not going to work. 2 and 9, 3 and 6. That's it. That's the full list. So actually this thing just isn't factorable. Put a box around it. Maybe X this out a little bit. We're stopping here. That's our answer. And moreover, we know that its range is all reals. So we're done. And that's it for function operations. So now they're asking which of the following have inverses that are also functions. Explain how you know. Basically, having inverses that are also functions just means you're a one-to-one function. So you just look. The graph of x squared obviously goes like this. Yoink. So we are obviously not one-to-one because the test for one-to-one is just the horizontal line test. And the reason why it's such a handy test is because we can see if our inverse is also a function. If I took this graph and reflected it, we've already seen this before, we'll draw it again anyway. But if I reflect this, then suddenly like the horizontal line at y equals 4, causing the red function not to be a one-to-one function, that line reflects. It becomes a vertical axis through the blue, showing that for that particular x value there's two different y values, which is exactly what a function can't do. So your easy test for who's got an inverse that is a function is you just run the horizontal line test and you check to see if it's one-to-one. So what are we saying? Which of the following I'm explain how you know? So not this one. So this is one thing you might say if you really wanted to be nice and clear. You'd say the inverse of function f is not a function because the regular, original function f is not one-to-one. That's super concise, but it's all you need, so that's what I would do. What about this? Square root of x minus 9, that would just be a square root function that's pushed 9 to the right. Yoink. Well, that thing passes the vertical line test, passes the horizontal line test too. So therefore it definitely has an inverse that is a function. That's it. All of these questions are as simple as, is the original function one-to-one? If your answer is yes, then its inverse is a function. So here we can say g inverse is a function because g of x is one-to-one. Now, they wanted us to do these by the equation, I guess. I'm gonna do it graphically. These next batch of questions is graphical already, which I think makes this easy. You just run the horizontal line test. This chunk of a sine graph, that's what this is, by the way. It's just sine of x with a couple modifications. But it doesn't pass, so you would definitely say here, this is function h. You would say h inverse, not a function, because not a function, because the original function h is not one-to-one. Now p, on the other hand, passes the horizontal line test. So we'll say p inverse is a function. Same reason, because p is one-to-one. Then I think there's even two more of these that try to take a numerical approach. So looking here, I mean, you could kind of plot these points real fast. And you can see that at 1 we go to 8. At 2 we're only at 6. At 3 we're at 4. At 4 we're at 3. At 5 we're at 10. And at 6 we're at 7. So looking at this, does it pass the vertical line test? Yes. And again, you can see that because all the x's only appear in the list once. Then you run the horizontal line test. Does it pass that? Sure. And again, you can see that because none of the h values appear more than once. So we can safely say that h of x is a function, at least as stated here. I should be saying h inverse. So h inverse is a function. You know why. It's because h of x is one-to-one. Now over here, can you spot what's wrong? 1, 2, 3, 4, 5, 6. We're not reusing any x values. That means we are going to be a function. 1, 2, 3, 4, 5, 6. But looking at the y values, I see 7 getting used twice. So the first value maps onto 5. Next one goes on to 7. Next one goes to 8. But then the next one maps onto 7 too. Next one to 6. Next one to only 1. So look what just happened right here. Those two data points, the ones that have 7, those make our lovely little function not a one-to-one function. We've failed. So if we took all these points and reflected them, then these two would become points that live on a vertical line, and we would fail the vertical line test and we would not be a function. So we're going to want to say t of x t inverse. Cool. All right, I think that means we're now done with the whole inverse thing. Nope. It says, how can you tell whether or not the inverse of a function is also a function? Inverse will be a function when original is one-to-one. We can also say when it passes the horizontal line test, but hopefully you know that that just means it's one-to-one. Which of the functions above are one-to-one? We already said not, yes, so B. No, yes, so B and D. Yes and no. So B, D, E. Yeah, we're done. Speaking of done, are we even close? I want to be close to done because I'm getting tired. It's also getting close to an hour. We got to do these prove algebraically ones, but the good news is anything involving sine or cosine we get to ignore because I'm not going to ask you about them. That means we only got to do 2. This first one looks pretty darn easy. We said to prove algebraically whether a function is even, odd, or neither, you're always gonna, this should have its name, but it doesn't. If this is f of x, then you're gonna find f of negative x. And then 3 things happen. You find this thing, and either that thing equals the regular old original function as if nothing happened, and that implies that you're even. Or this thing gives you the exact opposite of f of x. that little negative that you plugged in worms its way out to becoming just a single negative affecting the entire function, and that proves that your function is odd. And of course, secret option number 3 is that you just get something completely different. Oops. Anyway, so if you get something other than f of x or negative f of x, that implies that the function is neither. So let's do it. I'm going to shrink this down. Pause the video if you were planning on writing this down. Okay, now it's gone. So we said that to attack this problem, we're going to want to find f of negative x. And that's going to be 3 negative x to the 4th minus 4 times the absolute value of negative x. All right. So to give you a real firm algebraic way that you can do this, sort of for real, I showed you guys that you could take the negative sign that you're plugging in, break it down, treat it as an actual value. It's a -1 that we're multiplying by. And I suppose you could do that over here too. The rules of absolute value are a little different, but I think they'll work to our advantage. All right, then you know that when you're raising something to a power, when you're raising a product to a power, both of those factors are getting hit by that power. So this becomes 3 times -1 to the 4th times x to the 4th. And then I think we can just take the absolute value of these things separately. We could do absolute value of -1. We can do absolute value of x. And then what happens is -1 to the 4th becomes +1. It essentially cancels, and you get your 3x to the 4th right back. This negative gets washed away by absolute value. It becomes just a +1. So we basically end up with -4 times the absolute value of x all over again. And that's a good thing, because look, that's exactly the same as f of x. So we just proved that our f inverse gave us this, which is the original function. And so that proves that f of x is even. Then we can skip the sign one, go to this one, which I think we talked about in class in both periods, but that's okay. Again, you're going to want to let the x's, just do what the function says. We're going to plug in. We're always going to start by finding f of negative x, which for this is negative x over e to the negative x. And a lot of people just didn't remember how to handle negative exponents, but think of something like 2/3 to the -3 or whatever. The way I think about this is the -3, again, I would break it down to a -1 times a 3. Then I would break that down. Because when you're multiplying in an exponent, that's the same as having a power to a power. So I would now think of this as just a 2/3 to the -1 to the 3rd. And the effect of a -1 on the fraction is that it just does the reciprocal. So you now have 3 over 2 to the power of 3. And then cubing this would just be a numerator of 3 times 3 times 3, a denominator of 2 times 2 times 2. So if you actually were asked to do this, then you better remember those rules of exponents. So speaking of rules of exponents, looking at this, I know I could just rewrite this as 1 over e to the positive x. Then where do I go from there? It's not that hard. you keep the negative x. In the denominator, I would go ahead and raise both parts of this to the x. When you get 1 to the x, 1 to the x is just 1 all day long no matter what. 1 to the 7th is 1. So that's really just a 1. And the e to the x stays e to the x. And now we're basically looking at a complex fraction. You can pretend that this thing's over 1. But you know that complex fraction is going to turn into the numerator, which is negative x, just multiplied by the reciprocal of the denominator. So e to the x over 1, which gives us negative x times e to the x. So that's it. Looking at this, that is not the original function, that's for sure. The original function was x over e to the x. This is not the same thing. Moreover, it's not the opposite of the original function either. So it's neither. This function is neither even nor odd. Okay, and you don't have to worry about cosine, so we keep going. Neat. So this is the last page, last problem. And it's just a question about basic function properties. So if I ask you, the function has a horizontal asymptote at, has vertical asymptotes. Okay, so plural. We talked about this when we were doing this graph in the other setting, but it's at -4 and 5. It says the function is increasing for what intervals? So we're increasing when the graph's going up. So riding along this branch, we're going down. But as soon as we hit this branch, we're coming up. Then we hop up here, we're coming up. Now we're going down, and we're going down. So the only two intervals on which we increase are those two. And even though they both come together at -2, you do have to give your intervals as two separated intervals. So you better give your answer as -4 to -2. For the function is increasing for intervals. So I usually just say and. -2 to 0. Okay, got it. It now says the function is decreasing for what intervals? It's going to be everywhere else. Obviously this is decreasing. And then this is decreasing. This is decreasing. This is decreasing. And guess what? You kind of have to know calculus for this, but here where there's just a bend, we do not have to break our interval down into two separate intervals. Because here I'm decreasing, here I'm decreasing. You could give this answer to me as one continuous interval, but if you do know a little bit of calculus, then you know that this point here where the graph is rendered sharp, you can't actually do a derivative there, so you can't actually be increasing or decreasing there. So I think in the answer key I am going to give that as two separated intervals, but you guys should know that if you gave it as one smooth interval, I wouldn't be marking you down. Anyway, where are we decreasing? It's going to be from -infinity all the way to this vertical asymptote, so -4. And when else do we decrease? Right, so 0 to 1. When else? 1 to 5. And what else? This guy here is decreasing. So 5 to infinity. Now it's asking, does the function have an absolute max or min? It's a no, because we've got a branch right here that goes up, up, up forever. We've got a branch here that goes down, down, down forever. So no, there's no extrema. It says, is the function bounded in any way? If so, how? And it's not. I can go all the way up, I can go all the way down. So this thing would be not bounded. Then it says, what's the domain? Well, for domain, just read the function left to right. It might even help if you just kind of pick up your ruler. Because what I like to do is sort of just drag a big stick along. And see what I see. Put a handle on my stick. So anyway, as I drag this thing along, we can see that yes, the graph is defined here, 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 all the way going out that way. So our domain is going to be negative infinity up to, here's a break in the graph, it occurs at negative 4. Then my domain is going to be negative 4, da 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 da. Well, okay, here we get to a discontinuity, but the function is defined here. The function is defined to be negative 5. So negative 2 should be in our domain because negative 2 does actually give us some kind of output. Scrolling, scrolling, the next weird point. Sure, we don't get 3, but we do get 4. So is this function defined at 0? Yep. So 0 should be in our domain. Then you keep going. Everything's pretty normal, 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 till you get to the asymptote. That's going to cause a break in our domain. But then we run, 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 run. And then it's smooth again. So here where it says, what is the domain of the function? You're going to give me all these good bits. It's going to be negative infinity up to negative 4. Then you got to start at negative 4 again. This time running all the way to negative 2. But we don't need a break at negative 2. So we'll run all the way to 0. Yeah, sure. Okay. Then at 0, I'm not worried about this point as a domain element. It's clearly in our domain. So I'm going to keep running to 5. Then I'm going to run from 5 to infinity. I think that's the best way to do it, really. You just have to list all the intervals where the domain is working. What's the range of this function? Well, I see a branch that goes up and up and up forever, but it stops here. And I see a branch that goes down, down, down forever, but it stops here. So what about all this middle stuff? Well, as I look over, I see that this part is mapping onto 2, so 2 is in our range. Then all this is mapping onto everything from 2 to 0. This guy's mapping on to, well, all the way back down to infinity. So as I look this over, you've got the right idea. What's our range going to be? All reals. Because we go all the way down and all the way up. And I think I'm done, which is good because I'm tired and I'm losing my steam. But I'm going to push this out to you guys and you can start studying. Good luck.